Welcome to this presentation on Monte Carlo simulations using BatchSim. BatchSim is used for performing Monte Carlo simulations for investigating drug exposure at the population level to access the probability of target attainment. Using BatchSim has several benefits. Extended user-defined reporting by model instrumentation. Easily repeat an analysis run with different settings. High performance using parallel processing. There are currently no alternatives in the BatchSim platform. Wikipedia defines Monte Carlo methods as a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. The underlying concept is to use randomness to solve problems that might be deterministic in principle. They are often used in physical and mathematical problems and are most useful when it is difficult or impossible to use other approaches. Monte Carlo methods are mainly used in three problem classes: optimization, numerical integration, and generating draws from a probability distribution. The diagram in this slide shows several types of probability distribution functions. The most common distributions are the normal and the log normal distribution. A good metaphor for Monte Carlo simulations is rolling a dice a larger number of times, where each dice roll represents a draw from the probability distribution. The diagram below demonstrates the basic BatchSim workflow when using a single representative patient. The process starts with an BatchSim population model. We then instrument the model with instructions for report generation. The model is then ready for analysis using the BatchSim command line tool. The characteristics of a typical patient are contained in the population model. Only parameters with their fit property enabled will be randomized using the specified mean value and standard deviation. The results are captured in an Excel workbook which is automatically shown after completion of the process. This is a typical BatchSim command line. The diagram below demonstrates the basic BatchSim workflow when using a patient population. The process starts with an BatchSim population model and the population builder Excel tool PopGen. We then instrument the model with instructions for report generation. Patient data are generated using the population builder tool. It is also possible to use real patient data instead of generated patients. The model is then ready for analysis using the BatchSim command line tool. The population typically consists of 1,000 to 10,000 patients. Only parameters with their fit property enabled will be randomized using the specified mean value and standard deviation. The results are captured in an Excel workbook which is automatically shown after completion of the process. This is a typical BatchSim command line for running an analysis using a real or synthetic patient population. BatchFit and BatchSim require the .NET 6 runtime to be installed on your system. You will be offered to download and install .NET 6 if you launch BatchSim on a system without .NET 6 installed. Please note that this action requires administrator rights to complete. You can also download the .NET 6 runtime manually from the Microsoft website. Make sure you download the 64-bit version of the .NET 6 runtime. The BatchSim tool was created using .NET 6 because it allows for packaging the application into a single self-contained executable that can be easily copied to different project folders. The BatchSim application can be found in the BatchSim folder of the BatchSim installation directory. The BatchSim manual can also be found in this folder. The BatchSim executable can be copied to your working directory holding a BatchSim project. This folder typically also contains the EdSim population model and the PopGen population generation tool. We will demonstrate the BatchSim tool using a meropenem population model developed by Geisen et al. This model was published in the open access journal Infection and Drug Resistance in 2022. The population PK model parameter estimates are shown in the table below. The model only uses the creatinine clearance as a covariate as shown by this equation. A small TDM monograph is created for each model added to EdSim or MW-Pharm. This is the EdSim implementation of the meropenem model. We will now instrument the model with report instruction tags. The plasma concentration in the central compartment is given an alias name C1. This variable is also labeled with the simulation tag sim. Next, the AUC object is instrumented. The alias and label properties of interval AUC, absolute time above MIC and relative time above MIC are set. The label rep means that the variable will be reported for each dosing interval. The optional $postfix allows the user to specify a numeric reporting format. The instrumented meropenem population model can be found in the EdSim installation folder. We can perform a test simulation in EdSim before running the model using BatchSim. This allows us to see if the variables are correctly captured. Launching BatchSim with the help parameter will show a list of available options. We will highlight the most important options. Input files are specified using the P and X options. The Use P option to point to the EdSim model file. Use the X option to point to the patient Excel file. Use the N option to specify the number of simulations. This is equivalent to the number of patients. The default value is set to 1000 simulation. Use the C option to generate time series for all variables that were labeled with the sim tag. By default, the first patient is the population patient, which is not randomized as indicated with a blue color. Use the F option to overrule this behavior so that the first patient is also a randomized patient. The default output file name is report. You can change this name by using the R option. Use the M option to set the value of one or more symbols in the model. The format is objectName.SymbolName equals value. Multiple values must be separated by a comma. We start the Monte Carlo simulation using this command line. The progress of the analysis is displayed as a percentage and as an absolute count. Also, the number of parallel running tasks is shown. The maximum number of concurrent tasks is dependent on the CPU in your computer. A workstation with a dual Xeon processor with each 14 cores can run up to 56 tasks in parallel. Excel will be launched using the generated report as soon as the analysis process has been completed. The generated BatchSim report contains a number of worksheets. The PARM sheet contains a table of patient data and randomized parameters. The inputs sheet lists all administered dosages. For Curve 2 worksheets are generated. These represent the variables that were labeled with the simulation tag. The worksheet without the hashtag prefix contains the raw simulation output table. The worksheet with the hashtag prefix contains the graphical representation of the simulation. A worksheet is generated for each captured variable containing its value for each dosing interval. These represent the variables that were labeled with the report tag. This is the worksheet with the patient data and randomized parameters. Only variables that are labeled with the report tag are listed here. The data are listed for each individual patient. This is the patient data section. This is the total body parameter section. The effect of covariates is taken into account for these parameters. This is the model parameter section. These parameters are optionally normalized with respect to one or more covariates. The blue color of the first patient indicates that this patient represents the population. You can disable this with the F option, in which case the first patient will also be a randomized patient. Again, only variables that are labeled with the report tag are listed here. This is the worksheet with an overview of the dosing data. In the Population Builder tool PopGen, doses can be individualized using weight or body surface area. Please note that the same dose will be applied to all administrations. A separate worksheet will be created for all non-patient variables that are labeled with the report tag. In this example, the variable for the relative time above MIC. The probability of target attainment, or PTA, is calculated for the given threshold value in cell B16. The default threshold value is 0, in which case 100% of the patients achieve this level. This table shows the PTA in each dosing interval for increasing threshold values. There is no need to repeat the Monte Carlo simulation for each threshold level. Simply changing the threshold value is sufficient. This worksheet lists the captured minimum concentration in all dosing intervals. Here, the PTA threshold level in cell B16 represents the MIC. This table shows the PTA in each dosing interval for increasing MIC values. 100% of the patients achieve an MIC of 0.5 mg per liter. About 38% of the patient achieve an MIC of 2 mg per liter in the last dosing interval. 0% of the patients achieve an MIC of 4 mg per liter. This is the Excel formula for calculating the PTA. This is the BatchSim command line for running 10,000 simulations. The effect of the number of simulations on the calculated median AUC at steady state is shown in this graph. The real population value of the AUC can be obtained by simulating the population model in EdSim. The value can be found in the simulation output table of EdSim. 10 simulations are typically used for debugging the instrumented model. 100 simulations are typically used in the early trial phase. This can be increased to 1,000 simulation at a later stage. The final analysis is typically done with 1,000 to 10,000 patients. This worksheet demonstrates how the distribution of generated PK parameters can be validated. This example for the clearance parameter can be found in the BatchSim data folder. The clearance distribution is analyzed by creating a frequency table. The optimal bin size of the frequency table is calculated using the Friedman-Diaconis rule. The optimal bin size is then rounded to a convenient value, after which the number of parameters in each bin is counted. Also, the theoretical frequency is calculated using the Excel probability distribution formulas. The frequency table is typically visualized in a statistical histogram. The bars represent the actual parameter count in each parameter bin. The red line represents the theoretical parameter frequency based on the population mean and standard deviation. The calculated mean and standard deviation can be compared to the population values. This is the Excel formula for calculating the probability of value x for a given mean and SD using a normal distribution. Here W is the bin width and x the bin midpoint. This is the Excel formula for calculating the probability using a log normal distribution. Please note that pharmacokinetic parameters are typically assumed to be log normal distributed. The goal of generating a population is to also include the distribution of covariates within a population in addition to the inter-individual variation of the population parameters. The effect of one or more covariates is typically modeled as a correction factor applied to the parameter population value. The inter-individual parameter variation is defined for the population value. The inter-individual covariate variation is defined by the demographics of the population. Demographic data can be obtained from several sources, among which the United States Census Bureau. The PopGen tool can be used for building patient populations with specific demographic characteristics. The PopGen tool can be found in the BatchSim data folder. This worksheet shows the gender frequency per age group of the U.S. population in the year 2021. The PopGen tool has the equations for generating an age-compliant value for body height, body weight, creatinine level, and cystatin C level. Each of these variables can be randomized using a given bias and precision. Variables can be assumed to be normal or log normal distributed. Click the Run button in order to generate the actual patient population. The output is stored in the index worksheet. This is the index worksheet of the PopGen Population Builder tool. The data in this worksheet can be artificially generated or real data extracted from a patient database. The randomized ages in each age group are uniformly distributed. The dose for each patient can be individually established by including a dose column. The dose can be expressed in milligram per kilogram or milligram per square meter. In this example, the dose is expressed in milligram per square meter body surface area. We must first calculate the body surface area from height and weight using the Dubois and Dubois formula. Please note that we leave an empty column between the main table and the body surface area column. Now the individual dose for each patient can be calculated. The name of the dose column must use the object-oriented EDSIM symbol naming format, in which the name starts with the name of the input object IV and ends with the variable name dose, separated by a dot. Individual dosing intervals and infusion durations are not allowed, because in Monte Carlo simulations all patients must share the same timeline. BatchSim reports can be further analyzed using a number of tools. Post-processing scripts are usually created using the Python or R languages. The BatchSim report file is typically copied, after which it is reformatted for easy access using Python or R. We will demonstrate data post-processing using a simple one-compartment model. The model has only two parameters: volume and clearance. These parameters have values that yield a half-life of exactly 10 hours. We will now run a Monte Carlo simulation using 10,000 patients. The correlation between the volume and clearance will be increased for each Monte Carlo run. The data will be visualized using a Python script employing the well-known Seaborn libraries. The Python programming environment is very suitable for big data analysis. Powerful Python packages are Pandas for statistical data analysis and Seaborn for data visualization. The Seaborn library was used for creating a joint distribution plot of volume and clearance. The individual distribution of clearance and volume is shown on the secondary axis of this plot. The calculated half-life in each patient was plotted in a frequency histogram. The distribution of the half-life can also be plotted in a so-called box plot diagram. We sequentially created these plots for an increasing correlation value between volume and clearance. The first correlation was 0.01, which is equivalent to no correlation at all. The joint distribution plot is not a perfect circle because volume and clearance were assumed to be log-normal distributed. Log-normal distributions are highly asymmetrical when the average value approaches 0. The Monte Carlo simulation was repeated for a correlation of 0.10, 0.5, 0.9. and finally 0.99. Note how the joint probability distribution shape changes from a circle to an oval. In the extreme case of a correlation of 1, this would become a straight line. The variability in half-life gets smaller with increasing correlation between volume and clearance. In the extreme case of a correlation of 1, this would become a single value with no variability at all. We repeated the previous analysis using the HDR-CDE package that comes with the R environment. The histograms and box plots for the half-life generated by Python and R are identical. However, the joint distribution plot generated by the R script is clearly not correct. For this reason, we recommend the Seaborn Python libraries for performing this type of distribution analysis. The diagram below shows the folder structure of the BatchSim installation directory. The PY folder contains the Python demo scripts. The R folder contains the R demo scripts. The XL folder contains the Excel demo spreadsheets. These are the contents of each script folder. Please join me now for a hands-on exercise. Locate the BatchSim installation folder on your computer. Copy its contents to a new directory. This will be our working directory. Open the contents of the data folder in your working directory. The data folder contains the Meropenem model and the PopGen population generation tool. Go back to the root of your working directory. Open a command prompt here. Execute this command for performing a Monte Carlo simulation. The P option identifies the meropenem population model. The X option specifies the patient population data file containing 1,000 patients. The N option specifies that only 100 patients are used. The C option causes the variable time series to be generated. Please note that using the C option with a large number of patients may result in very large report files. This workbook represents the generated report file. The variable time series data table is stored in worksheet C1. The variable time series chart is contained in worksheet #C1. You can have a look at all worksheets. The #C2 worksheet contains the chart of the concentration in the peripheral compartment. The upper line represents the upper limit of the 95% confidence interval. The lower line represents the lower limit of the 95% confidence interval. The line in the middle represents the median curve. The displayed cell ranges can be used to convert the 95% confidence interval into a colored area. These ranges must be associated with the y-error bars of the median curve. This is explained in detail in the BatchSim manual. The chart below displays the result of using the median y-error bars for representing the 95% confidence interval. The confidence range can dynamically be changed by setting the upper and lower limits in the source data table. Changes are directly reflected in the chart. Thank you for your attention. I hope you have enjoyed this BatchSim workshop. Please consult the BatchSim manual for more detailed information.